In the previous lesson, we saw that if a function is calling itself with reduced value of n, then the reduced value can be n minus 1 or n minus 2 or n minus 3, or in general it can be n minus b, where b is a constant which is greater than 0. We learned how to solve such recurrences in the previous session. The general equation of these recurrences was Tn is equal to a times t of n minus b plus some function of n, where both a and b are greater than 0. But what if the value of n is reduced by n by 2? Which means that first time when the function is called for the value of n. Next time when the function is called, it is called for value n by 2 or n by 3 or n by 4 or in general n by b. In this video, we will be looking at functions whose time and space complexity can be represented by the equations like Tn is equal to a t of n by b plus some function of n. The function that you are looking at your screen right now is the function for quicksort. This function sorts the array A from low till high. The initial value of low is 0 and initial value of high is a dot length minus 1. So if an array is of length n, then this function will be able to sort that array using quicksort algorithm. As you can see, this function calls another function which partitions the array. So this function picks one element as pivot and it partitions the array in two parts. In best case, these two parts will be equal. If Tn represent the time taken by this function, we know that the partition logic takes order of n time, and then we are calling the quicksort function for n by 2. So this will take time t of n by 2. Even this will take time t of n by 2. Therefore, the recurrence for this function will be sum of all of these. We can say that Tn is equal to 2 times t of n by 2 plus order of n. If you compare it with the general equation, then a is 2, b is also 2, and function is n. We can again discuss the two methods. First is the function call method and second is the substitution method. Let us first discuss the function call method. Initially, the function is called for n. Then from this function, the function is called for n by 2 and n by 2. Now, how much time are we taking at level 0? At level 0, we are performing this condition check and we are calling the partition function which is taking order of n time. Therefore, total time taken at this function is n plus 1, which is again order of n. So time taken at this function is n. How much time is taken at the next level? At the next level, there are two function calls. And both of these function calls will take n by 2 and n by 2 time. Therefore, we can say that the total time taken at this level is also n. Now what will happen is that these two functions will call the same function again for n by 2 square. Time taken at this level is also 4 times n by 2 square, that is again n. We will keep on dividing n by 2 till n by 2 raised to the power k becomes equal to 1. When n by 2 raised to the power k becomes equal to 1, then we will hit the terminating condition and the terminating condition will just return from there, taking constant time. The total number of levels in this function called tree will be k, because the denominator will become 2 raised to the power k only after k levels. If you solve this equation, n by 2 raised to the power k is equal to 1, which means that 2 raised to the power k is equal to n, which further means that k is equal to log of n to the base 2. The total number of levels are log n. At every level we are taking n time. Therefore, the total time taken is n log n. And that is the solution of this recursion. We can say that t of n is big O or theta of n log n. Now let's solve it using the substitution method. T of n is 2 times t of n by 2 plus n. Then t of n by 2 will be 2 times t of n by 2 square plus n by 2. Now if you substitute this blue equation in the black equation, then we will get t of n is equal to 2 times 2t of n by 2 square plus n by 2 plus n. This part is coming from the previous blue part. So this is the blue part. If you open these brackets, you will get t of n is equal to 2 square t of n by 2 square. These 2 and 2 will cancel each other and we will get 2 times n. If you further substitute, we will get this is equal to 2 cube t of n by 2 raised to the power 3 plus 3 into n. So after k steps, it will become equal to 2 raised to power k plus t times n by 2 raised to power k plus k into n. We will stop when this becomes equal to 1, which means that we will stop when n by 2 raised to the power k becomes equal to 1. N by 2 raised to power k will be 1 when k is log of n to the base 2. If you replace this k by log of n to the base 2 here, then we will get that Tn is equal to some constant plus n log n. Therefore, this will be big O of n log n to the base 2. This is how we are solving it using the substitution method. Look at the function of merge sort and compare it with quick sort. In case of merge sort also, we are dividing the array in two parts and then solving the two parts individually. And after solving the two parts individually, we merge them. So merging takes order of n time. Therefore, the recursion for merge sort will also be Tn equal to 2 times t of n by 2 plus order of n. And the time complexity of merge sort will also come out to be Tn is equal to n log n. You must have seen the binary search function. Following is the recursive implementation of binary search function. This function search in array A from low till high for value VAL. Initially, when you call this function, the value of low will be 0 and value of high will be n minus 1, indicating the first index and the last index. The first condition is to terminate the recursion. When low becomes greater than high, it means that we have traversed the entire array and we have not found the value. In that situation, we will return false. Otherwise, we will find the middle element, which is at low plus high by 2. I understand that this can be further optimized because the intermediate value of low plus high by 2 can go out of the bound. But we are not considering those optimizations because in this course, we are focusing only on the recurrences. So we find the middle element and there are three possibilities. First possibility is if the middle element is equal to value, we return true from here itself. Otherwise, we will either search on the left side or on the right side of mid, which means that if initially the size of the array is n, then next time when the function is called, either we are calling for the first half of the array and discarding the second half, or we are calling the function for second half of the array and discarding the first half. In any case, in the next iteration, the number of elements will be n by 2. And how much time is every function taking? So every function will perform this condition check, every function will do this computation, every function will also check these conditions. Therefore, the total time taken by the function is constant. Initially, the function is called for n. We take constant time in this function and then call the same function for n by 2. This function will also take constant time and then again call itself for n by 2 square. This function will also take constant time and then again call itself for n by 2 raised to the power 3. This will continue until n by 2 raised to the power k becomes less than 1. So when this becomes less than 1, it means that k will be order of log of n. It means that total number of function calls will be log n. We have seen this earlier also. This is essentially halving the parameter. So we have seen how the exponential growth and exponential reduction happens when we are doubling and halving. So in case of halving, the number of times the function will be called will be log n. This is how we are finding the time complexity of binary search using the function called tree. Now let's first try to find the recurrence of this function and then try to solve it using the substitution method. Let us assume that the total time taken by this function is Tn. Inside this function, we are taking constant time and either we are calling this or we are calling this, but not both of them. Therefore, the function will be called for t of n by 2 and all of these statements will take constant time. Therefore, the equation will be Tn is equal to t of n by 2 plus some constant. Now you can easily solve it. Why? Because you just need to substitute t of n by 2. T of n by 2 is equal to t of n by 2 square plus some constant. If you substitute it here, then we will get t of n is equal to t of, should be n by 2 square plus 2 times the constant 1 and 1. We will keep on adding this constant until n by 2 raised to power k becomes equal to 1, which will be the case after log n steps. It means that for log n times, we will keep on adding 1. So how many times are we adding 1? Log n times. It means that the time complexity will be order of log of n to the base 2. Let us write one more recurrence. T of n is equal to T of n by 2 plus n in case n is greater than 1, and this is equal to 1 in case n is less than or equal to 1. So this is how generally we should be writing the recurrences. In our situation, we are writing it like a shortcut. We are not mentioning the terminating condition because in most of the cases the terminating condition is assumed. But if you want to write full recurrence, then you should be writing it like this. Can you find a function whose time complexity is represented by this recurrence? You must have seen the problem where you are given an array and a number k, and you have to find the kth largest or kth smallest element in the array. To solve this problem, you use the partition logic of quicksort. The partition logic of quicksort takes n time, and in the next iteration, the size of the array is reduced by half. Therefore, this is the recurrence for that. Now, how do you solve it? Again, there are two methods. Either you can solve it using the function called tree, or you can solve it using the substitution method. If you solve it using the function called tree, then initially we call the function for n. At this level, we are taking n time, which is same as this, and then call the function for n by 2. At this level, we will be taking n by 2 time and then calling the function for n by 2 square. At this level, the time taken will be n by 2 square and the function will be called for n by 2 raised to power 3. And we'll keep on doing it until n by 2 raised to the power k becomes equal to 1. It means that we will be calling it log n times. Therefore, the total time taken by this function will be sum of these numbers. The total time taken will be n plus n by 2 plus n by 2 square plus n by 2 cube plus n by 2 raised to power 4 plus so on. Now this is a decreasing GP. The sum of a decreasing GP is big O of the first term of the GP, which is big O of n. If you want, you can take n common, and then we will be left with 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on. Now the sum of these numbers will be equal to 1 plus 1, that is equal to 2. So 2 is the upper bound for this, which means that the entire equation comes out to be 2n, hence order of n. So this is how we can solve it using the function called tree. Now if you want to solve it using the substitution method, you will probably get the same equation. First we will write T of n is equal to T of n by 2 plus n. Then we substitute this T of n by 2 and write this is equal to T of n by 2 square plus n by 2 plus n. If you further substitute it, you will get n plus n by 2 plus n by 2 square. And if you keep on substituting it, you will get the same equation. And when you find the sum of this equation, you will find that T of n is big O of n. In all of these recurrences, I'm calling it big O, but you can call it theta also. Since during the interviews, you will be more using the big O terminology, that's why I'm using the big O terminology here. Now let's understand the master theorem for recurrence equations where n is getting divided by a constant. The general equation is T of n equals a times T of n by b plus function of n. Now this function of n can either have a power of n, or it can have a power of log n, or it can have both. So let's write this function of n as n raised to the power k into log of n raised to the power p. If fn is only n, then p is equal to 0. If fn is log n, then k is equal to 0. If fn is n log n, then both k and p are 1, and like that. Therefore, let's replace fn by n raised to the power k log n raised to the power p. In this case, there are four constants: a, b, k, and p. What can we say about these constants? A has to be greater than 0. In this case, b cannot be 1, because if b is 1, then we are not reducing. So b has to be greater than 1. And both k and p can be any integers. So k can be negative also, which means 1 by n, and p can be negative also, which means 1 divided by log n. To solve this recurrence, you need to find two numbers. The first number is log of a to the base b, and second number is k. So k is already given, and we find log of a to the base b. So log of a to the base b. We just need to find log of a to the base b and compare it with k. When you compare it with k, there are three possibilities. First possibility is that log of a to the base b is greater than k. Second possibility is log of a to the base b is equal to k. And third possibility is log of a to the base b is less than k. So these are the three possibilities. Either log a to the base b is greater than or equal to or less than k. Let's look at these three possibilities. If it is the first case, then answer is simply big O of n raised to the power log of a to the base b. So we have already found log of a to the base b. If this value is greater than k, then answer is simply n raised to the power this value. So this is the first case. Consider the following example. Tn is equal to 2tn by 2 plus 1. In this case, a is 2, b is 2. If you represent this one as n raised to the power k plus log of n raised to the power p, it means that k is 0 because n raised to power 0 is 1 and p is also 0 because log n raised to power 0 is also 1. So first we will find log of 2 to the base 2. Now we know that log of 2 to the base 2 is equal to 1. If you compare it with k, this is greater than k, which is equal to 0. So because this is greater than k, we can conclude that Tn is equal to big O of n raised to the power this value, which means n raised to the power 1. Therefore, this is equal to big O of n raised to the power 1. What if we have an equation like this? Tn is equal to 4tn by 2 plus 1. In this case, log a to the base b, which means log of 4 to the base 2 is 2 because 4 is 2 raised to power 2. So this is 2, 2 is greater than 0, which means that this will be big O of n raised to the power 2. So you can see that we are just ignoring the function or fn. Let's say if this is Tn is equal to 4t of n by 2 plus n. In this case, log of 4 to the base 2 is 2, which is greater than k because k here is 1. Because it is greater than k, the answer is again big O of n square and fn will be completely ignored. So for this also, the answer is big O of n square. The difference between them will be in terms of their constant factor and not in asymptotic terms. What if you have an equation like this? Tn is 4t of n by 2 plus log n. Again, log of a to the base b is 2 and here k is 0. P is 1 but k is 0. So again the time complexity will be big O of n square. So this is the first case. Now let's come to the second case. Second case is when log of a to the base b is equal to k. If this is the case, then we have to look for value of p. So consider value of p and compare it with minus 1. Again, there are three possibilities. Either p is greater than minus 1 or p is equal to minus 1 or p is less than minus 1. Remember, here we are comparing it with minus 1 and not with 1. So it is either greater than minus 1 or equal to minus 1 or less than minus 1. The second case represents when fn is a function which is having log of n in the denominator. Only then p will be equal to minus 1. The third case represents when you have log n in the denominator and the power of this log n is greater than 1. Let's say log square n. And the first case represents when either log n is multiplied or log n is not multiplied. So the first case is when you do not have log n in the denominator. So if you have log n in the denominator, then it will have some effect. If you have a higher power of log n in the denominator, then we will completely ignore it. If you have a positive log n in the numerator or you do not have log n, then we will have log n here. Therefore, in the first case, the answer will be Tn is equal to n raised to the power k into log of n to the power p plus 1. If in the numerator you have log square n, then this will be log cube n. If in the numerator you does not have even a single log n, then this will be log n. If in the numerator you have log raised to the power 5n, then this will be log raised to the power 6n. So we just need to multiply one extra log n in the function, because the function is n raised to the power k log of n to the power p. So we are just multiplying one extra log n. In the second case, where you have log n in the denominator, Tn is n raised to the power k log of n. So here, because you have log n in the denominator, we are multiplying n raised to the power k with log of log n. And if you have a very high power of log n in the denominator, then we will completely ignore log n and we'll say that Tn is big O of n raised to the power k. So let me repeat it again. You compare log of a to the base b with k. If they are equal, then you check for the value of p. P means power of log n in the function. If power of log n in the function is 0 or positive, then we keep the function as it is and multiply it with log n. So this is nothing but function multiplied by log of n. If you have log n in the denominator in the function, then we will just ignore the denominator, keep the power of k and multiply log of n. And if you have a higher power of log n in the denominator, then just ignore the log n and only keep the power of k, only keep the power of n. Consider the following recursions. T of n is equal to T of n by 2 plus 1. Now here a is 1, b is 2. So what will be log of 1 to the base 2? It will be 0. And k is also 0. It means that log of a to the base b is equal to k. If these two are equal, then we need to consider the power of p. What is the power of p here? The power of p is 0. If power of p is 0, we just need to multiply function with log n. It means that the solution of this recursion is big O of log of n. Consider another recursion. If it is T of n is equal to T of n by 2 plus log of n. If this is the case, again, log of a to the base b is equal to p. Both of them are 0. So we just need to multiply function with log of n. So the solution for this will be order of log n into log n, which is log square n. What if we have Tn is equal to T of n by 2 plus 1 by log n? Here also log of a to the base b is equal to k is equal to 0. So both of them are 0. So we need to consider p. In this case, p is equal to minus 1 because we have log n in the denominator. So if you have log n in the denominator, then you just need to multiply the numerator with log of Therefore, this is big O of log of n. What if we have Tn equals T of n by 2 plus 1 divided by log square n? In this case, again, log of a to the base b is equal to k. So we consider p. In this case, p is equal to minus 2. Because if you bring log n to the numerator, the power will become minus 2. Because minus 2 is less than minus 1. Therefore, we will ignore the denominator and this is big O of 1. What if the equation is Tn equals 2Tn by 2 plus n? In this case, a is 2, b is 2. So log of 2 to the base 2 is equal to 1 and k is also 1 because power of n is 1. Therefore, this is the second case. You consider the value of p. In this case, p is 0, which is greater than minus 1. So if p is greater than minus 1, then we just multiply function with log of n. Therefore, this comes out to be big O of n log n. And we have also seen that this is the recurrence of both quicksort and merge sort. And both of them comes out to be n log n. What if you have Tn equals 4Tn by 2 plus n square log square n? In this case, a is 4, b is 2. So if log of a to the base b, log of 4 to the base 2 is 2 and k is also 2. So this k is also 2. Therefore, log of a to the base b is equal to k. Value of p is 2, which is greater than minus 1. If it is greater than minus 1, then we just multiply this function with log n. Therefore, this entire Tn is equal to big O of n square log square n into log n, which means log cube n. This is as simple as this. Now let's come to the third case. The third case is when log of a to the base b is less than k. If this is the case, then you again find the value of p. But this time you check whether p is positive or negative. So if P is positive, which means that it is greater than or equal to 0. In computer science, in most of the cases, 0 is considered positive. In mathematics, it belongs to the set of non-positives and non-negatives. But in computer science, in most of the cases, it is positive. So you find the value of P and check whether it is positive or negative. If P is negative, which means you have log n in the denominator, then we will just ignore log n and Tn will be big O of n raised to the power k, which is the numerator. And if P is positive, then Tn will be big O of n raised to the power k log of n raised to the power p, which is nothing but the function itself. So if you have log n in the denominator, then you just ignore it. If you do not have log n in the denominator, then answer will be equal to the function itself. As simple as this. Let's consider some examples. Tn equals t of n by 2 plus n. In this case, a is 1, b is 2. So log of 1 to the base 2 will be 0 and k is equal to 1 because we have n here. So clearly log of a to the base b is less than k. If it is less than k, it means this is the third case. So in the third case, we do not have any log n in the denominator. Therefore, the solution of this recurrence will be big O of function itself, which is big O of n. And this is the recurrence of the solution of the problem where we are finding the kth largest element in the array. What if the recurrence is Tn equals t of n by 2 plus n divided by log of n? Because log of n is in the denominator, so we will just ignore it and this will also be big O of n. What if we have Tn equals t of n by 2 plus n log square n? In this case, because we do not have log n in the denominator, so we keep the function as it is. This is big O of n log square n. Consider one more example. T of n equals 2t n by 2 plus n cube divided by log square n. Again, a is 2, b is 2. So log of 2 to the base 2 comes out to be 1. So the first term is log a to the base b, which is 1. K in this case is 3. Log of a to the base b is less than 3. We consider the value of p. Because we have log n in the denominator, we ignore the denominator and this is equal to big O of n cube. I hope you may have realized that the master theorem is not as difficult as it appears to be.